So we're going to do a little intro today on um, what we will find out as parametric equations, skipping around a little bit. And got a little, hopefully, creative with my intro, trying to mix things up a little, but we'll see how it goes. So starting off here, we so far have really only done algebraic equations where we have an input and an output, right? Kind of a basic relationship. So like something like y equals x squared. And this implies for us, right, that y depends on what x is. So if x is 2, y is 4, right, x is 3, y is 9, so on and so forth. And we literally call them independent and dependent variables. But we never think about, well, maybe y just coincidentally happens to equal what x squared is, and there's something else going on here. Some, I don't know, a hidden factor maybe you could think about. So kind of thinking about that, I have this little scenario here, and I opened up a beach shop, right? Nice little beach shop. And I sold two main things at my shop: sunscreen and ice cream. And you could check out this little chart for a minute. And hopefully we see that there's definitely some kind of relationship here, right? It looks like as my sunscreen values over here are going up, my ice cream values are also going up, right? Like maybe we could pick out the highest. It looks like my best sunscreen is 90, and that's also my best ice cream, 1,156. Whew, must have been a busy day, right? So let's say this is like a week at my beach shop. So looking through, maybe we could relate these somehow, right? So let's take a second, and I don't have audience participation right now, but pretend you're here, right? Just call it out in your bed, in your wherever you are, right? So checking out the sunscreen, is there anything that you notice about all those numbers we got going on there? Right? Hopefully you're screaming at your camera. When I look at them, to me, I'm like, well, they're all divisible by 3, right? Oh, 33 is 11 times 3. 45 is 15 times 3, right? 8 times 3. You got a lot of times 3s going on here. All right, kind of see what's going on there. So we could say, like, I'm going to call sunscreen S, and ice cream I'll call capital I. So sunscreen is divisible by 3. I'm going to write that over there. All right, what about ice cream? Any thoughts on those? Take a second to look down that list. All right, and maybe hopefully you're screaming out, well, it looks like we've got some perfect squares going on, right? 225 is 15. Oh, that was a weird number. 15 squared, 144, 12 squared, 121, 11 squared. All of them are perfect squares. The other ones might not be as obvious going through. So I'm just going to throw them in this equation here. Our ice cream squared. Well, actually, I'm going to go this way. They're all perfect squares, so we could take the square root of them all, right? And then let's relate those kind of like base numbers, I'm going to call them 11 and 15. 8 and 12, 7 and 11, right? Those are related. If I take that base number 15 and add or subtract 4, right, I'll get 11. 12, subtract 4, get 8. 11, subtract 4, get 7. So if I take that square root ice cream number and subtract 4, we've got that sunscreen value divided by 3. Right, so thinking about those, we just created a relationship between sunscreen and ice cream. And in fact, we could make it so like our normal equations that we've seen, sunscreen, like in terms of ice cream. And thinking about what that would be, that's if I write an S equals equation, that means sunscreen would equal 3 times the quantity, square root of ice cream, minus 4. Now, I hope you're thinking this makes perfect sense, right? Sunscreen depends on my ice cream sales. If I sell 225 ice cream bars, cones, whatever it is, I'm obviously going to sell 33 sunscreens, right? No, I hope you're screaming at your camera. This is ridiculous. Why does my sunscreen sales depend on my ice cream? Or why would my ice cream sales depend on my sunscreen, right? That doesn't matter. And maybe you're thinking now that there should be some like missing link in here. So let's think a second. And this is like, if we were in the classroom, I'd be like, all right, let's think about what could relate. And we probably have some people screaming out crazy weird things, but then I think a lot of us would be screaming out. Hopefully you just screamed it out. Maybe temperature, right? Or the weather of the day. So I just happen to have in my pocket here what the temperature was for all of these days in my beach shoppe. So I'll add them in here. This guy was 71 degrees, and these are Fahrenheit for us. We have 55, 75, 50, 68, 90, 67, and 80. So now we kind of have this root cause, right? It makes sense more so, I think, that if it's a warm day, I'm going to sell sunscreen and I'm going to sell ice cream. So let's think about maybe how we can now relate these numbers to our ice cream sales, our sunscreen sales, and our ice cream sales to the temperature outside. So take a second and let's write our sunscreen in terms of temperature and our ice cream in terms of temperature. My hint, and I want you guys to take a minute and actually try it out, is gonna be to think about these like base numbers we have here, the 15, the 12, 11, the 8, the 15, right? All those when we did like the divisible by 3 and stuff going on. So take a second, you can pause me and see if you can find the relationship between those. All right, but I am going to move forward and do it here. And I'm going to start looking at comparing the sunscreen. Oh, that's not the marker I wanted. Comparing the sunscreen numbers first with the temperature numbers. And since we're writing in terms of temperature, I'm going to actually start with the temperature. Like, so 71 down to 33. 55, notice that the zeros, I might skip over those right now because it seems like something's funky going on. We've got zeros and a 55, zeros and a 50. So let's concentrate on the other ones. So we've got 71 to 33, 75 to 45, 68 to 24. But like I said before, really let's compare with these numbers we have over here because 71 to 11, 75 to 15, 68 to 8, I think there's an easier relationship to go with. So if we take our temperature number and subtract 60, right? 71 minus 60 is 11. 75 minus 60 is 15. That'll give us this base number, and then we can multiply that by 3. So we have our sunscreen in terms of temperature. All right, let's do the same thing for our ice cream numbers. So maybe 71 to 15, 68 to 12, 67 to 11. Let's just try the whole subtracting things first, see if it works. So 67 to get down to 11. I'm going to compare these two. We would need to subtract 56. Does that work for these guys? And I think it does. So if we take the temperature, we subtract 56 and we square it, we've got our ice cream sold. So this is kind of that hidden, I want to call it like correlation or the hidden factor, right? That really both of these depend on. And it makes sense. Now let's go back to those zeros, right? Those don't make sense. They don't fit this mold I have over here. And that's where like our real life application comes in and what we have to do with these. So if we think about our equations, right? This guy over here is our ice cream sales, and he's a parabola. It'd be a parabola with a 0 of 56. So if I sold, or if the temperature outside was 55 degrees, think about how many ice creams I'm selling. It's going back up, right? That would be 1. If it was 54 degrees, I'd sell 4, right? If we got down to 0 degrees, I would sell 56 squared. Now that doesn't seem to make sense, right? So I think for these, we'd also need to put some domain restrictions on here. So maybe we'd say for this one, t would be greater than or equal to 56. But same thing with this guy, right? Nice linear equation. We'd have a line with a 0 at 60 that goes up. So T's temperature, this is saying if I'm below 60 degrees, I'm going to sell negative sunscreens. Again, doesn't make so much sense. So maybe we're saying T is greater than or equal to 60 here. And we'd have to decide, right, which of those restrictions we'd want to go with. And kind of like we did for, losing my words here, when we did composition of functions, right? You go with usually the most restrictive. So probably, and again, we're making this up, this one is what we'd go with. All right, so maybe the zeros, how can I make sense of those? Maybe if it's 60 degrees out, I close my shop. I don't think it's worth staying open. Or, I don't think anyone's going to buy ice cream or sunscreen, or it was a rainy day, some things that might come into play for real life situations. All right, so now thinking about what this is really, right? What we have here, it's a measurement that works with or beside the other measurements, and that's kind of an important value. We call that a parameter. And that word literally breaks down to, right, para is beside, meter is a measure. So it's a measurement that goes beside other measurements, that sticks with kind of what we have going on. We've seen hopefully these words before in math, just some other examples, give you guys some knowledge bombs here. Is that what you call them? Right? How about parallel lines? That literally means lines lel beside each other. How about this, one of my favorites, parabola, right? So bola, I think, is Latin word derived from ball. Like they have some correlation. I'm not a Latin student, just math, right? But think about like if you throw a ball, right? If you throw a ball right up and down, it's just going to make a line. But if you throw a ball sideways, you'll get a parabola. So to throw beside is parabola. So a little couple things there. Some other examples of, things that have parameters, but we have to be careful out there because, there could be situations where they try to purposely trick you by not giving the parameter, or maybe we're missing the root of the cause of what's related. So some other examples that exist out there might be like the number of TVs a society has is related to obesity. So the more TVs a society has, the fatter the society is. Makes sense, right? Now, either you're laughing or you're saying, yeah, kind of makes sense, right? Think about America. You could probably count the number of TVs in someone's house and think about they're related to obesity. And if I asked the parameters, we would have some good laughs in school right now, right? But I think probably the best parameter that relates these is money for a society, right? If you have more money, you can buy more food, you can buy more TVs. Who knows? Maybe you're not, getting outside, you're sitting on the couch, but usually that is like an example of a parameter there. One a little more morbid, but again, a connection that's been made is the more wealthy a society is, GDP, for those out there with their econ, right, gross domestic profit, the more cancer the society gets. Again, I said a little morbid, right? So, you're getting rich and then you're dying of cancer, right? Again, kind of sad. And maybe we're waffling a little too. That doesn't make sense, right? There's got to be something in between. And the parameter here would be longevity, which I'm not spelling right, but that maybe the society is living longer, right? So the more money you make, the more you can afford medical bills. You could live longer, right? If you're not making enough money, if you're not wealthy, if you don't have health insurance, you're probably dying of, when you get a little bit older, the flu or some other things that they can't pick up. So unfortunately, that is another relationship. One of the most common parameters we'll see out there and we'll use for most of our examples is time. So I'm just going to put that by itself. Right, so a little intro to parametric equations here. We have actually dealt with a set of parametric equations, and these guys were parametric equations. So it's any two equations that can be represented as a function of a parameter of another independent variable. So an example for us might be x equals sine of theta and y equals cosine of theta, right? And when we correlated these go through, we did actually graph this, right? Think about x and y. If we put a 0 in for x and y, sine and cosine, we're going to get 0, 1. If I put 90 degrees in, right? Sorry, I get 1, 0 originally. I'll get 0, 1, and that would graph the unit circle, right? Which, think about our regular rectangular form, x squared plus y squared equals 1, which is where we are going to link all of these conics. So I'm going to leave you guys off with that. I know it's kind of a longer video, but hopefully you got an idea of what parametric equations are and what they represent. And we'll go on to some examples today.